periodic table. And here I said this is semiconductors. Okay, so in this chapter, we are going to discuss bonding. So one important feature to form bonding is the electron activity. Sometimes you can say electron positivity, which is the same, right? So if we align our periodic table with the axis to measure the electron activity, so as this arrow goes red, it means the electron activity got increased, right? And goes to blue, that means the electron activity goes to very, very small. That means here, see if you remember the name, alkaline material, alkaline metals, they have the smallest electron negativity. That means it's very electron positive. If an element is very electron positive, it so much want to just give away the electrons, right? Give away the valency electrons, okay? And goes to here. See, this is an incomplete periodic table, okay? So I remove this pink. I remove this pink column, inner gas column, because it's stable. When it's stable, it's neutral, okay? So it doesn't really want to lose or gain any electrons, so I remove this one. So this is a partial periodic table. So the rightmost column is halogen. So halogen is the most electron negative column here. And if you just look at the column from fluoride to all the way like indium or like AT, I don't know how to pronounce that, the electron activity gets decreased. So this height, okay, somehow tells you the relative electron negativity for each of the column, okay? And if you look at each of the row, we call it series. So the fluoride, oxygen, nitrogen, and like carbon, boron, the electron activity like get decreased as well, okay? And here it's very interesting that for the semiconductor here, their electron activity actually quite similar to each other. Also, within transition metals, their electron activity are quite similar as well. Until you reach the boundary, there's a sudden drop to the alkaline metal, okay? So here, the color somehow tells you that within those zoom, the electron activity somehow is quite close to each other. And here, this zoom, the electron activity is high. And the blue zone is like the ocean, the electron activity is very, very small. That means it's very positive. Okay, so if you print this graph in your mind, actually that implies the way how bonding can form and how different bonding can form from different places from periodic table. That's why I give you the periodic table, you can always look at that. Okay, so last time, or maybe in the first lecture, we discussed three main categories of materials: metals, ceramics, and polymers. We do not discuss composite. We do not discuss the metal materials. We just discuss monolithic materials, right? So here, from the periodic table, this chapter will tell you how do you form each type of this compound, okay? For metals, I called it in yellow, right? That means anything like yellowish can form metals and alloys. So this is how do you interpret this slide, okay? So for ceramic, as you can see, I have this kind of gradient. That means for the positive side, you can choose from like a little bit red or, you know, magenta color kind of element from periodic table. And from the right-hand side, I put like purple blue. So you just choose from the purple blue, okay? Let's forget about inert gas. They just, you know, independent in their own group, okay? So we just look at here. So that means if you take some element from this color and you take some element from this color, you form ceramics from periodic table, Okay? I think this exactly coded similarly, except I just separate the transition metal from the alkaline earth. Okay? Okay, so polymer. I put polymer in blue. Okay, as you can see, that's hydrogen, carbon, nitrogen, phosphorus, sulfur, and oxygen. Right? So those elements form polymer. Okay? So now from different color that you can locate on the periodic table to form different categories of materials that we learned. Okay. But this is still like very, very high level. So how do elements from different places form the compound that yellow, like gradient color, like blue color? We will discuss that later. Okay? So that really goes to the main point of this chapter, atomic bonding. Okay. So atomic bonding divides into two parts, primary bonding and secondary bonding. Of course, to form compound, we focus on primary bonding. So that bonding is a strong bonding. That means the bonding energy is very, very large. So the two atoms can be together like in a stable state. So if you want to remove them, you need to pay energy. What do you mean by pay energy? You have either heat it up or make mechanical work, right, to break them, but need a lot of effort. Secondary bonding means the bonding energy is relatively weak compared to the primary bonding. That means you don't need to pay much effort. You don't need to pay much energy to break such bonding. So that's two differences. And today, hopefully we can cover the three types of the primary bonding, depends on the time. Okay, we still have a lot of time for ionic bonding, covalent bonding, and metallic bonding. Hopefully, if I finish like the lecture, you can easily tell if I give you a compound and through their location from periodic table, you can tell me like what types of the bonding. So that's the whole point, okay, for this chapter. Okay. So how a bond can form between two elements, two atoms. Actually, they can form through so-called interatomic interaction. They can be the same species, like carbon. They can be different species, like magnesium, oxygen, right? So each of them, you can see them as like a core. This core can be a general core. Right? We say this is the atomic structure. It has a nucleus, and it has this kind of electron orbitals, right? So here we use the core combined with the nucleus and its inner shell as a new core. And this is the outermost shell. Participating in bonding, the outermost shell plays an important role. So we only look at the outermost shell because it's like furthest away from the positively charged nucleus. So it has a very weak attraction from the nucleus. So inside, the electrons still spin around, but it has like a stronger attraction from the nucleus. But the atoms here is relatively free. So people call it free electron. Okay? They are free electrons. They can easily go away or can easily, jump in, right? So usually the interaction to form bonding is the interatomic interaction between the outermost free electrons for certain electron negative and certain electron positive elements. And then we put them together to form this bond. And this bond is like a spring. We call it a potential energy. Not sure if you remember what is the potential energy. Potential energy, a simplest way to image a potential energy means it's an energy that you cannot see, but there's a potential there. Okay? So it's like if you have something on the ground and you lift it up, you can say, oh, the potential energy increase, but you cannot really see that energy. Okay, so that's a potential energy, and that potential energy acts as an absorption or repulsion, depends on the distance. And then at a very comfortable distance, they can be stable, equilibrium, and form a bond. But here, I put a spring here, but in fact, in real world, there's no such kind of spring. Okay, so depending on the distance between A atom and B atom, the bonding force can be repulsive in this direction or attractive in this direction. And here is how people quantitatively calculate the force. The total force will be the sum of the repulsive force and attractive force. And people just do experiments. I don't know how the experiment was conducted. Just imagine there's such kind of experiments can really measure the quantity of the force that like in this direction or in this direction. And then they plot the force of the repulsive force versus distance. This is the separation, distance from one to the other. And the repulsive force usually has value and then decrease to zero at some point and decrease very, very fast, right? And for the attractive force, well, it just only has value when the two atoms are far away from each other, and they decrease more gently than repulsive force. And if we add this red dashed lines for repulsive and attractive force, then we come up with this total force curve. Different material will have different such kind of curve. So that means different types of elements from periodic table will have different bonding strengths, correspond to different bonding lengths that form the whole diverse compounds in this world. Okay, so here there's a point here correspond to zero force. So that means the material can be in equilibrium. And here, if the force is too high, it wants to go to here. And if force too high, it wants to go to here. And for repulsive force, by convention, is the negative sign. And attractive force, by convention, is the positive sign. Okay? That's the equilibrium. And people call it equilibrium separation. Use a symbol R0. Okay, so what is the relationship between the force and energy? So this is the only calculation in this chapter. I believe this will be much simpler than fluid mechanics. Okay. I don't have gradient, I don't have divergence. I know some of you also take fluid mechanics. I only need you to do the full differentiation, okay? So the relationship between force and energy is just the differentiation, okay? The force is defined as a derivative of potential energy with respect to separation, okay? So here, this has been already differentiated. At equilibrium correspond to force equals to zero. So that corresponds to what value of the potential energy? Extreme value. So in general, if you have a function in terms of x, and if something is the derivative of f with respect to x, and if this one equals to zero, you can solve for x. You call it x0, such that what? df dx evaluate at x0 equals to 0. Then, what is this value? This is an extreme value. It could be minimum, could be the maximum, but it's an extreme value, right? Okay, I promise this is the only differentiation that you need to do in this chapter, okay? So you just need to know there exists a function. This function is called potential energy, but you don't know the expression of it, right? But you know this function is a function of x. So here, x means the separation between two atoms, r, okay? And then you take derivative of this function with respect to position. That gives you force, okay? At equilibrium, we know that force must go away, right? So this force equals to 0. From pure math, we know that the first differentiation equals to 0 correspond to the extreme value, and here correspond to energy minimum value, okay? How do you find the equilibrium? So, as I just showed, you need to take the differentiation of potential energy with respect to separation distance and find what value solves this equation, right? And substitute that value back. You'll get the equilibrium of the bonding state. Okay? So that's the only math you need. And go back to material science. Okay, so why do we care about this? Why do we care about bonding? Because bonding closely relates to properties. What properties? Melting point. If the bonding energy is high, that means you need to pay more energy to break it. That corresponds to like higher melting point, right? Elastic modulus. So if you want to, like, I don't know, maybe some of you will do mechanical test. So you'll have like a sample that you have so-called universal test machine to pull it until it breaks. So if you want to break something, you need to pay energy. So this is like mechanical energy, right? So if the Young's modulus or elastic modulus is very high, that means it's very hard to deform it elastically. So that also relates to the bonding property, bonding length and bonding energy. And also like thermal expansion and some other property like electric resistivity also. But that's like more advanced, right? Okay, so here is how we really calculate it. So if you have an expression of potential energy, okay, suppose you have it, and how do you get the force? You take the differentiation of potential energy with respect to separation r. You get the force. But if you have the force expression, how do you get to the potential energy? You do the integration, okay? So you do the integration, you get the potential energy. And here is a schematic plot of potential energy, okay? And equilibrium separation, so if you solve force equals to 0, you get equilibrium separation. You substitute this value here, and you calculate the corresponding value here. That corresponds to a energy well. That corresponds to the minimal energy state. We know that in this in nature, nearly every compounds that we find, they're all in equilibrium. If they're not in equilibrium, they tend to go to equilibrium state. Thermodynamics drive, right? Okay, so we call it equilibrium. And just to give you some example, different material will have different bonding energy. That bonding energy somehow relates to like how much work you need to do to break this bond. That means what? That means you want to have some atom sit here, very nice. And if you want to do work to bring it away, how much energy you want to pay? You want to pay this much energy, right? This is the amount of energy. So like far away, we assume this is 0. So here, this value tells you the bonding energy. So that means this is meaningful, right? So if you got this one, you substitute back into the expression of the potential energy, you calculate how much work you need to do to break that bond, right? Okay, so here we have some examples. We have sodium chloride, okay, one from this side, the other one from this side. They can form a compound, and you need to pay this much, kilojoule per mole, okay? And correspond to melting temperature around 800 Celsius, okay? And here you have this one. Chloride can form bond as well, right? And it has a very small bonding energy, okay? And it has a small melting point. But notice that they're not linear. They're not so close to relates to each other, but the bonding energy somehow can give you some guidance. But I'm not saying they have this very strict linear relation. For example, if you have this diamond, right? Diamond is what? Is carbon-carbon bond. Carbon-carbon bond. And their bonding energy is even higher, right? And that corresponds to very high melting point. Okay. If you go to the textbook, you'll find the counterexamples. Okay? You'll definitely find the counterexamples with like smaller bonding energy, but with like a higher melting point. That's why I say this is not completely linear, but here it just gives you a rough idea. Like how easy or how hard you bring these equilibrium atoms far away somehow relates to like the bonding energy, how strong and how weak the bonding energy between two atoms. Okay? Any questions? Okay. Let's look at like how stiff and how elastic materials according to their different like potential energy or different force, interatomic potentials, okay? So if we want to ask like how hard the two atoms can be pulled away from their equilibrium to like very, very infinitely far away, so I have this red and blue, okay? And here I have A atom and B atom. A corresponds to the red one, B corresponds to the blue one. Which one will be like more stiff? Stiff means hard to deform, okay? Not stiff means easy to deform. Like rubber, very easy to deform. Like stainless steel, very hard to deform. Okay. So from the force, we can draw the bonding energy. So for this one, how do you draw the bonding energy? The bonding energy is here at the zero force. Here at the zero force, that corresponds to the minimum. And this minimum corresponds to the slope. Here the slope is higher. That means it has like deeper energy well. And this slope is not so stiff, so it has a shallower energy well. So that means if you have like atoms, if you have atoms here, you need to pay more energy to bring it far away. But for the blue one, you need to pay less energy to bring it far away. That means here, sometimes the bonding length is shorter, implies that the bonding energy could be stronger, and that corresponds to a higher melting point and more stiffer material. Okay. Again, this is not a generally true, or this is not a universally true thing. So detailed argument still based on the profile of this force versus R. So when you graduate, if you got chance go to graduate school, in physics department, there's like a whole branch of research topics relates to the calculation of the interatomic potentials for different elements. When the elements get more and more complicated, then this kind of behavior will get more complicated. So the point is still people look at the people examine the values here and examine the values here. And sometimes people also look at the second derivative of it. The second derivative of it means like how to say, like how narrow or how wide this kind of energy well. So people also discuss the geometry of this energy well. So that corresponds to the second derivative. But in this course, I hope you have this kind of rough understanding. If I give you an expression of potential energy, how do you calculate the equilibrium? And how do you get the equilibrium separation? And how do you count the minimum value to form a bond, right? Okay, so here, let's review the valency electron definition again. So here I said we have the nucleus and we have this inner shells. All together, we have a new core. And we only look at the outmost valency electrons, and they are very, very important because they participate forming the bond in chemical reaction. Okay, so for example, you need to look at the outermost electrons. And fortunately, you have this like very tiny little value here to tell you what is the outmost value of the valency electron for each of the element. Okay, something like that. Primary bond number one, ionic bonding. Ionic bonding formed between the rightmost and the leftmost element in periodic table. More precisely, they formed from the typical metal and the typical non-metal. And they have very big difference in electron activity. Okay, so that's the definition of ionic bond. And here, give you some example. The examples are alkaline and some of the alkaline earths from like right-hand side, rightmost, and some like non-metallic, like oxygen, like fluoride, chloride, and sulfur, those type of elements. Here is the mechanism. The mechanism to form the bond, of course, is a so-called interatomic potential. Right, this type of thing. But since the element property from different places in periodic table are different, so the property, the physical property of interatomic potential also is different. So for ionic bonded compound, the interatomic potential is so-called Coulomb attraction. That's because the element to form them has a very big difference in electron negativity. Such big electron negativity is just like a positive negative charge. So in your high school or middle school, right? Middle school physics, if you have positive negative charges put together, that's Coulomb attraction. So which is the same here in material. So if you have a strongly positive ions and strongly negative ions you put together, their interaction has the physics called Coulomb interaction. And here people give them a name. For positively charged one, we call it cation. For negatively charged one, we call it anion. So usually you'll see in papers or somewhere else, people call it oxygen, fluoride, people call them anions, right? And people call like lithium, we call it cations, okay? So that's just the terminology, you get used to it. And the force, people call it Coulomb force. And if this is Coulomb force, you'll have a very explicit way to write the formula for f of x. So here is the formula for that. Okay, so now you have the potential expression. Once you have the potential expression, that's a function of r. So you can take the derivative with respect to r to get equilibrium separation. And then substitute back to this expression, you get the energy, right? You get the energy to form such kind of ionic bonding. Okay. So in this formula, you'll have some constant. This is the permittivity in vacuum, and this is the charges of one electron. And depends on the valence electron of the specific cation and anion, you have Z cation and Z anion. And for sodium, you have 1. For calcium, you have 2. For aluminum, you have 3. And for this Z anion, again, for oxygen, you have 2. For chloride, you have 1, right? So if you know all of those, you get the value. Okay. So the formation mechanism is that you have an array, periodic array, to form the crystal. And each cation neighboring by the anion, each anion neighboring by the cation. And how do they form this kind of interaction? The cation loses this electron completely and give it to the anion. Anion receive it completely. And each of them become stable E configuration. Okay, so this is the formation mechanism for ionic bonding.